Welcome to our enzyme mechanisms series. We're going to begin with a discussion of the terminology of mechanistic chemistry, especially that portion of the terminology that's relevant to enzymes. We're going to look at the kinds of chemical reaction types in enzyme catalysis, some of the commonly observed aspects of chemical reaction types. We're going to look at a couple of enzyme types as well. I use the term archetype here. Serine proteases is our go-to example of enzyme mechanisms, but we'll see a few others. And throughout it all, we'll be reviewing this idea of affinity and specificity between substrate and enzyme as exemplifying the kind of complementary interactions that drive all protein function. So let's begin with the idea of arrow pushing, which is something we're all familiar with from our organic chemistry backgrounds. And I'm using arrow pushing in this first example of nucleophilic catalysis, or nucleophilic attack. So this is a standard kind of enzyme reaction that we'll see frequently. There's some kind of nucleophile here, and it attacks this carbonyl carbon. This is particularly relevant to our serine protease discussion. And the nucleophile, the presentation of those electrons at that carbonyl carbon causes this rearrangement. So we lose electrons from our carbonyl bond, and those go up to the oxygen. And here we see this unstable structure, this oxyanion formed, and we have this structure that's formed. And then because it's unstable, that collapses and those electrons go back. We retrieve our carbonyl, and then we kick out something. Now it could be that the nucleophile that came in was kicked out, but in this case, the leaving group is the X group is a better leaving group than the nucleophile that attacked, and so it's kicked out. So again, our arrows go from our electrons to where the electrons want to be. In this case, at the carbonyl carbon. And let's see, here's another example wherein we are using an electrophile to begin the catalysis. Now this is an interesting example because in the end what we wind up with is not an electrophile but a nucleophile. But the electrophile serves to the function of activating a water molecule. Okay, so the water molecule binds at this zinc atom. This is probably a zinc 2+. This is probably the active site of carbonic anhydrase, which I'll refer to again in a few minutes. It's the zinc ion itself is bound by a few histidines. These are histidines here, and then of course that's a strong electrophile, a cation like that, and it binds this water molecule, and that polarization increases the acidity of this proton, and it pops away. It deprotonates and results in the formation of a hydroxyl, which is a good nucleophile now. So this I'll repeat several times, something activated this nucleophile, and this electrophile served to activate this nucleophile. So that activation is something that we'll see again and again as well. But we want to be familiar with how to draw these arrows to help us rationalize the enzyme mechanisms that we're proposing. Another key concept is the idea of the transient intermediate. And I've sort of conflated the transient intermediate with the idea of a transition state here. Let's refer to our textbook section 6.5, figure 6.5, to think about structures of transition states. But let's come back to this idea. Again, tetrahedral carbon here, nucleophilic attack going on. We don't know what activated this nucleophile, but it's performing a nucleophilic attack at this carbon. Population of an unstable transition state in the form of this sort of pentacoordinate carbon immediately collapses to form another tetrahedral carbon, this unstable, this more stable, and again, X here being the better leaving group, the electrons go back to it and it's kicked out. And then we have modified our carbon with this nucleophile. The key point for this bullet is that this structure is the transition state, and it is stabilized by the enzyme. We've talked about this before. Something about this structure that would not be formed with any great frequency in the absence of enzyme is stabilized by the interactions present in the enzyme's active site. What I want to be careful about, though, is when we're looking back at figure 6.5 is we don't want to oversell this idea of transition state stabilization too much, although we'll see some great examples of it, and it is very important. But let's remember, too, that the substrate and product on and off rates, their affinities, will also be important, especially in specific cases. So this is a general rule. We stabilize transition states, but there are complexities there as well. Another thing I want to emphasize before I leave this slide is the idea that an intermediate is distinct from a transition state. An intermediate is something that's observable kinetically. And if you look back at that figure 6.5, you'll see the population of the enzyme substrate complex. That's an example of our intermediate. In this case, it might be something that's actually physically observable, whereas a transition state traditionally is considered to be populated with such a low frequency that it's not something that we can experimentally get a handle on. If it was, we'd probably call it an intermediate. Okay, here's a great example. I've stolen this picture from colleagues at Arizona, but the work originally was done back in the 70s by Keenan and Alworth. You can go look this article up if you want. The basic idea here is this transition state stabilization and how we might probe that notion experimentally. Here we are looking at an enzyme called proline racemase. Of course, as you might guess from the name, proline racemase interconverts L-proline and D-proline and is proposed to do it through this planar transition state. So here's a hypothesis now that we can probe. Let's look at the reactant and product. We see here that we have this non-planar structure. We've got, again, a tetrahedral carbon here, and we look at the configuration of functional groups around that carbon. We assign it an L or a D, depending on what they are. Let's focus particularly on the carbonyl, since that's what we'll just focus on that. But that's relevant to our transition state structure, where we lose a proton, and the transition state then is this planar structure where the carbonyl carbon is still present. The carboxylic acid carbon is still present. But then the proton comes back in a different configuration, and now we're a different enantiomer. Let's think about how we would probe that experimentally. Well, if the stabilization of the transition state is how the enzyme works, then we might imagine that we could design some molecules that look like the transition state. They're not the transition state. They're structurally very, very similar. Here we have two pyrrole derivatives. I'm going to remind you that when we were studying heme proteins, we saw that the heme iron is bound by the tetrapyrrole of the heme itself. So 4 of these pyrrole molecules going to make up the heme. In this case, we see that we got 2 different varieties of pyrrole that you can take a look very similar to the proposed transition state. And in fact, when you probe their inhibition, you see that these are very potent inhibitors of proline racemase. Whereas if we construct a similar molecule that's a tetrahedral analog, again reminding us that we're referring to this carbon here. This is also an inhibitor, but it's very, very poor, not a good binder. So we would say that in the case of proline racemase, it looks as though the transition state is indeed planar, as evidenced by the effectiveness of these inhibitors. Now, you could poke some holes in that if you like, thinking about the details of the structural differences. In particular, is there something about this oxygen that might make this a poorer mimic of the substrate or product or transition state? Arguable, but I think it's hard to argue the key idea here being that it appears that in this case the transition state is planar and is what is being stabilized by the enzyme. Cool story. Okay, let's think about a couple of enzyme mechanisms and we'll dive right in. What I'm wanting to get at here is how we generate reactive species in enzyme active sites. So the bullet point is just bond cleavages frequently result in the formation of reactive species. Let's look at a few different flavors. Carbanions. This in particular is enolase, which this is described in some detail in your textbook. I'm not going to go through the whole reaction here. This is part of one of your homework assignments as well, though. We generate a carbanion. Here's a substrate, right? We see it's this 3-carbon carbohydrate. It's phosphorylated at the 2 position. We've got a carboxylic acid here, hydroxyl here. Let's look at what's happening at the level of the enzyme. First of all, presentation of a couple of active side chains. This glutamic acid involved in a hydrogen bond with one of the substrate hydroxyls. Looks like it's anchoring it, stabilizing it in this configuration. Looking over here, we got a couple of magnesium ions bound. I'll remind you, enolase is a tin barrel. Oftentimes we see metal ions bound in the tin barrel structures. But in this case, those metal ions serving to, again, coordinate some chemical element, functional group of the substrate, anchoring this carboxylic acid group. Finally, and this is, I'm saving the best for last, enolase presents this lysine, which is a nice base. We all know what bases do in the Bronsted-Lowry sense. And in terms of our action here, we're abstracting a proton from this carbon, and what we see is the electrons eventually go to reside transiently at this carbonyl oxygen. But what I haven't quite shown you here is that for a very brief period, there's a population of a carbanion at this carbon. So a negatively charged, the electrons reside at least for a little while at this carbon, and that's relevant to the mechanism. We won't go any farther than that. But again, the point through all of this being that the enzyme serves to activate something. And in this case, we're activating the substrate generation of a transient carbanion. We can also form carbocations. In this example, I think all of these examples were swiped from Wikipedia if you're interested. Isopentenyl diphosphatase, here's the 1, 2, 3, 4, 5, right? See how the branching gives us isopentenyl diphosphate. I think you get the idea. Diphosphatase. In this case, there's a lot of interesting stuff going on that will be useful for referring to future slides. But first, let's just point out that what's happening here is that we're adding this proton across the double bond. Now, the arrows go from the electrons in the double bond to the proton, but normally we'd think about this as adding the proton across the double bond. And now you see that you've gone from this methylene to a methyl group here. But the key is that at this carbon, at least transiently, we populate a carbocation. And in this case, we'll call it a carbocation intermediate, probably because we can observe it experimentally. So carbocations are relevant, and you can see, you can easily imagine why these very reactive species are interesting components and critical components of the enzyme mechanism. Before I leave this, though, I'm just going to refer to this A for acid. What do acids do? They donate protons. And also relevant to this structure is B, a base that's going to act as a general base, abstracting this proton. And we see this is, again, we'll see this over and over in enzyme active sites, just as we did in the case of enolase a second ago. Finally, though, let's look at an example of a radical generation. And this enzyme is cytochrome P450. A little bit of background. It's interesting background. Cytochromes P450 are a collection of enzymes present in metazoans that are relevant for elimination of toxins, right? Or xenobiotics, often they're called. This can include poisons, but they can also include drug molecules. So these enzymes act oftentimes, not strictly, but oftentimes by hydroxylating the substrate, making it more water soluble. So you could imagine that plays a role in either the direct excretion of the drug molecule or else activating it for subsequent modifications by other enzymes, but always involved in the detoxification of drug molecules and other molecules, other xenobiotics, anything foreign. The key here being that they do so through the activation of an oxygen radical. And you might imagine, what does this look like to you? A bunch of paroles binding an iron. Interesting here now in the cytochrome P450, we're liganded not by a proximal histidine, but by a sulfur, right? A cysteine side chain, very, very cool. But of course, at the heme, we're going to bind an oxygen. Now, everything that happened at the front end of this enzyme, I'm not describing. Of course, the dioxygen is broken in the beginning part of this reaction, and with the result being that we form this radical, right? A free electron ready to engage with many, many possible substrates. And of course, we can define what substrates are acted upon where? In the enzyme binding site, in the enzyme active site. So in this case, it doesn't really matter what this substrate is. The key is that we create a bond between the radical and this proton at this carbon, essentially abstracting the proton, and then that activates the carbon itself to abstract the hydroxyl, and then we go from this protonated carbon to this hydroxylated carbon, and then we're ready for another oxygen to bind. And you see that there's an oxidation state change, blah blah blah. But the key here is that we use radicals in a couple of different places in this reaction mechanism to drive the reaction forward. Again, the key with all of these being the formation of reactive species